Welcome to Section 3 of Unit 12, Integration by Substitution. In this section, we are going to look at how we integrate composite functions, functions within a function. And we're going to use a technique called substitution. So before we do that, let's just take a look at a simple integral here of the integral of cosine of x dx. Now, we know that the integral of cosine of x is simply sine x plus c. And we know that if we take a derivative of this with respect to x, so if we take a derivative with respect to x of sine x plus c, we get back to cosine of x. All right? Well, this may lead us to believe that if we want to integrate cosine of 2x dx, that it's just going to equal sine of 2x plus c. But we find that if we take the derivative of this, if we take a derivative of sine of 2x plus c with respect to x, that actually we get a 2 cosine of 2x. And that is not the same as the cosine of 2x. Now, we've learned a quick little rule with these trig functions earlier that whenever we have a linear coefficient inside of a trig function, we just multiply by the reciprocal of that coefficient to take care of it. And I explained to you that that just takes care of the chain rule. All right, but we didn't really go into any deeper reasoning, which that is true that the integral of cosine of 2x dx is simply 1/2 sine of 2x plus c. And so it's just explained as, well, if you take the derivative, this 2 is going to pop out and it needs to cancel out. Okay, well, that's as far as we went before, but now we're actually going to dig into the idea behind this. So let's say we have a function, let's get rid of that there. Let's say we have a function big F such that big F prime of x is equal to little f of x. All right, and let's say we have a function inside of big F that we're going to call g. So we have a composite function big F of g of x. Okay, this could simply just be a polynomial inside of a trig function, or just a polynomial inside of something being squared or raised to a power, anything like that. All right, well, if we want to take a derivative of this with respect to x, we know that we have to use the chain rule, that we take the derivative of the outside function, so that's big F prime, and we still have that same g function inside of that, but then we have to multiply by the derivative of that inside function, so we multiply by g prime of x. Well, this is simply going to be, if this big F prime is f of x, little f, we can say that this is just the composite function of little f of g of x times g prime of x. Now, this may not seem all that significant. It may just be, well, hey, yeah, that's the chain rule. We've done that already with derivatives. But this little rule here is actually very helpful to us in that we can go backwards. If we have the integral of some composite function, but we have the derivative of the inner function hanging outside with our differential, well, we know that's simply going to equal the antiderivative of this outer function of our inner function. And so that gives us a capability of integrating these products of functions if they align to a certain situation. Okay, so let's look at this formally here. And let's say that we're going to introduce a variable u, and another term for this method of substitution is actually u substitution, because we use the variable u a lot to simplify things. So we're going to let u equal that inner function g of x, and we're going to assume that g is continuous on an interval and f is continuous on that same corresponding range of g. So g has to be a continuous function, and then when you get the outputs of g, those are the inputs of f, and f needs to be continuous on the range of g. And then what that means is on that interval, if we have the integral of f of g of x times g prime of x dx, then we can say that's just simply the integral of f of u du. And this looks like a much nicer function in that when we integrate that, that's just going to be our antiderivative of f, assuming that big F prime is equal to f of u plus c. Okay, so let's look at a procedure that we're going to use here with all of these types of substitution problems. So in these substitution problems, we're going to be given an indefinite integral involving a composite function. So that's the first tip. If you have a composite function, a function within a function, then you may need to use substitution. Okay, so you have to identify the inner function. Whatever the inner function is, you're going to call that u. And that is going to be your substitution part. All right, and you have to identify u such that a constant multiple of g prime appears somewhere in the integrand. And you're going to see this a little more closely when we go over some examples. But then we actually do the substitution. We make u equal to g of x and du equal to g prime dx in the integral. And then we're going to evaluate the new indefinite integral with respect to u, because we simplify it to a form that we can integrate. And then we're going to write the result in terms of x using this original substitution that you did. So you're going to undo the original substitution. Now, this is an important disclaimer. Not all integrals yield to the substitution rule. Okay, this is going to help us expand the ability that we now possess to integrate, but this isn't going to allow us to integrate absolutely everything. It just is going to allow us to integrate more than what we can right now. So let's take a look at an example here of the integral of 2 times the quantity 2x plus 1 cubed dx. And so we have to identify, is this a composite function? And yes, we have an inner function of 2x plus 1 being cubed, the outer function is being cubed. So let's identify the inner function and call it u. So u is equal to 2x plus 1. Now the trick is, what is du? If u is 2x plus 1, then du is going to be the differential. Well, how does 2x plus 1 change with respect to x? Well, that's going to be a 2, but then we got to keep that differential dx out here, and the derivative of 1 is just 0. So we identify that, well, this 2x plus 1, what we have here is actually u cubed. All right, so this right here is talking about u cubed. And then what we have left is a 2 and a dx, so that represents our du. So essentially, we have the integral of u cubed du. Okay, we have to make sure that we account for everything in our integral. We've got the 2x plus 1 cubed, that's u cubed, the 2 dx, that's du. Well, we can evaluate this integral and say that this is going to be 1/4 u to the 4th, all right? And don't forget our plus c. And now we want to undo the substitution that we did originally. Well, we originally said u was equal to 2x plus 1. So let's put the 2x plus 1 back in and say that this is going to be 1/4 times the quantity 2x plus 1 raised to the 4th plus c. Okay, we don't have to change c because c is just some constant of integration and it's just going to remain classified as c. If we happen to take the derivative of this, we find that using the chain rule, this 4 will come down as a coefficient, cancel out the 1/4, and that will be raised to the 3rd power, and then take the derivative of the inside, and that gives us a 2. And so we end up with 2 times the quantity, 2x plus 1 raised to the 3rd power. So this is our antiderivative, or our general form of the antiderivative, the indefinite integral of 2 times the quantity 2x plus 1 cubed. All right, now let's look at another example. Okay, we have x to the 4th times the quantity x to the 5th plus 6 raised to the 9th. Now, both this and the previous example could be done without substitution, but it takes some binomial expansion and then the distributive property to get us into a big polynomial that we could integrate, but then would be a lot tougher, and then we'd have to figure out how to simplify it later and recognize that it's still a binomial raised to a power, and it's just going to create a lot more work for us. So using substitution can help simplify and get things done more quickly. So let's identify the innermost function. And in this case, the innermost function is going to be the x to the fifth plus 6. So that's what we call u. U is x to the fifth plus 6. Well, what's du? If that's u, then du is 5x to the fourth dx, and then plus 0 because derivative of 6 is 0. Well, right here, we have x plus 6 raised to the ninth. So that is going to be u to the ninth. But if we look at what's left, we have an x to the fourth and a dx. So this right here is not du. It's a fraction of du. It's close. It's got the key components. It has the x to the fourth and dx. But du is really 5 times that quantity. We only have 1 times that quantity, so we have 1/5 du. And that's the important part, understanding that we have 1/5 of our du. So our integral here is actually going to be the integral of, and I'm going to put the 1/5 out front because if it's a constant, I'll put it out in front of the integral. 1/5 of the integral of u to the ninth du. So now we have that 1/5, and we can integrate u to the ninth. Well, u to the ninth just gives us 1/10 that pops out, and we're multiplying by u to the 10th plus c, and we make our substitution again, and we end up getting 1/50th of the quantity x to the 5th plus 6 raised to the 10th plus c. And that is the indefinite integral here. Once again, take the derivative, apply the chain rule, you'll see that it comes out to what we had in our integrand. Now let's look at a trig function here. Let's say we have cosine cubed x times sine x dx. So these might be a little more difficult to identify. Well, what's u? Do I say sine x is u, or do I say cosine x? So we have to identify what is the inner function. Well, cosine is actually being cubed here. So let's say that cosine is our u. So cosine x is u. That makes du a negative sine x dx. Okay, let's not forget the negative here. All right, so if u is cosine x, du is negative sine x dx. So let's identify what we have. Well, we have our u being cubed, so this is u cubed. But then what do we have left? We have close to our du, but actually we have a negative du, because du is a negative sine dx. This is a positive sine dx. So what we have in our integral is a negative du. So this is really the integral of u cubed du, but it's the negative of it because we have a negative du. So this gives us a negative 1/4 u to the fourth plus c. Undo our original substitution, and this is negative 1/4 cosine to the fourth x plus c. Take the derivative of that, and we will wind up with our original integrand of cosine cubed x times sine x. All right, so what this does, this actually opens the door to integrate a few of the trig functions we have left. Actually, 4 of the trig functions we have left. Up until this point, we don't know how to integrate or find the antiderivative of tangent, secant, cosecant, or cotangent. So now we can. The integral of tangent. Well, let's rewrite this and say it's the integral of sine x over cosine x dx. And so let's use u substitution here, and we have to identify what's the inner function. How is this a composite function? And you might think, well, it's not a composite function, it's a quotient of 2 functions. And yet, it is a composite function. We have cosine as our inner function being raised to the negative first power, or we have 1 over cosine. So cosine is actually our inner function here, so we're going to say u is equal to cosine of x. So once again, du is going to be a negative sine x dx. So the same exact substitution that we had in the last problem. So what do we have? Let's identify. Well, this is actually the integral of 1 over u du, but we have the negative of that. Now, why do we have the negative? Well, this 1 over cosine here is going to be our 1 over u, but the sine x dx is close to our du, but it's just a negative of it. So that's why we have negative du. So when we evaluate this integral, we get the negative of the natural log of the absolute value of u plus c. So we go back to, well, what's our original substitution? U is cosine of x. So this is equal to the negative natural log of the absolute value of cosine of x plus c. Or if you want to get tricky with it and say that, well, this negative sign really raises that to a negative 1, it's the natural log of the absolute value of secant x plus c. Either one is sufficient. And in fact, this is something that you may want to write on your trig identity sheet to say that the integral of tangent of x dx is equal to one of these two here. What I'd like you to do for an assignment here tonight is to first evaluate the integral of secant x dx, the integral of cosecant x dx, and the integral of cotangent x dx, so that you can have all of these along with your integral of tangent on your trig identity sheet. And then in addition to that, I want you to look on page 338, and you're going to do 3 problems here, number 1, 5, and 11.